So we'd talked a little last time about the bode plot. Maybe we just kind of happened into that because we were working on reviewing our algebra and whatnot for transfer functions and said, well, hey, here's what you can do with a transfer function, and ventured into it that way. We may want to be a little more deliberate about this, so we'll back up a little bit and talk about this. First thing might be the name. Some people you'll hear pronounce it bode, some is bode. I've heard it both ways. I guess I'll pay tribute to that and probably pronounce it both ways throughout lecture. So, but probably most of the time I'll call it a bode diagram. But you'll hear people that are doing it both ways. If we look at a circuit, okay, and we look at putting a signal into a circuit like we've done on some of those filters or something like that, and then look at what we get out of that. So we take a series arrangement or whatever arrangement you want, put a signal into it, and then get a signal out of it. And we look at the transfer function as the ratio of the output over the input. Then we can get an expression that we can try and plot, or specifically plot with the bode diagram. Oftentimes, the way this thing looks, our transfer function, we could probably make this look real mathy and whatnot, but the transfer function here, if I look at the magnitude of it, it's going to have some numerator in the S domain and some denominator in the S domain. And really, this boils down to probably a polynomial. We'll see this. So we might talk about some constant a sub m, S sub m plus a m minus 1, S m minus 1 plus, and so on, till you get up to a s plus a naught. And you could do the very same thing for the denominator, different symbols, b sub n, s sub n plus b n minus 1, s n minus 1 plus, and so on. Being very general with this, b sub 1, s1 plus b naught. The ratio of two polynomials oftentimes is what you have. And when you get the factors of these, you could factor them a variety of different ways, partial fractions or something like that. You'll probably have a constant here, we'll call that k naught, and then you'll have these factors, s minus, we'll say z1, and then s minus z2, and so on, depending on how many terms you would have, s minus zm. And in the denominator, we won't have a constant in the denominator because we could just combine that with a constant in the numerator and just have one constant. So then have s minus p1 and s minus p2, and so on, s minus pn. Okay, and that looks pretty mathy. Looks like we've cracked open a math book there. But by definition, these z's would be our zeros. Okay, and then these terms down here, when those go to 0, that's a little more problematic in our expression. That would be the poles. Okay, so we're going to talk about zeros, and we're going to talk about poles. And the bode plot is a good way of plotting those. Whether the curve goes along and turns up, whether the curve goes along and turns down, like we saw last time, we'd have those zeros and poles. So we could spend a lot more time talking about that if we wanted to. I guess by definition, with the bode plot, then when we did the bode, we looked at doing the decibel plot, which put the amplitude of this on a decibel scale, which by definition was 20 times the not the natural logarithm, but the base 10 logarithm of the absolute value or the magnitude of that transfer function. Okay, and we went through that. So when someone talks about poles and zeros, I just wanted you to be aware of what that was. Well, with that at hand, probably we can just start through some examples. We did that one problem, and we'll see that again. I'm going to come back and visit that in a little bit as we talk about trying to deal with how accurate these straight line approximations are. But maybe we'll start with a very simple problem and try our hand at that. So let's say And I guess I need another piece of paper here. So, I think I was going to just try and put this right on the graph, yeah. So I'll start with this. Do I have the log paper or the semi-log paper the right way this time? Yeah, I think I do. So that's good. Let's say that we have a function that looks like this. Let's say that I want to try and do the bode plot for this, and I'm going to say that I have k naught times the absolute value of 1 plus j omega over 0.1 divided by omega times, and I should use the absolute value here. I'll just use absolute value because I'm looking at the magnitude of 1 plus j omega divided by 5. Okay, so I've got fairly easy, quite a bit easier polynomial than we were talking about just a moment ago with all those terms. A fairly easy polynomial here. And let's say that k naught is equal to the square root of 10, so probably due to the values of the inductors, resistors, or something like that, that comes up like that. And that's just a term that's going to be easy to handle mathematically. Probably in real life it'd be some odd decimal. Z1 is, let's see, we have the 0. Where's our zeros? What's when omega is equal to what? 0.1? Up in the numerator, when omega is equal to 0.1, things are interesting, right? Okay, it's going to turn and on that. And then where's our pole? We have a pole at 5, don't we? Okay, and these would be radians per second. Okay.
There's a pole and a 0, a frequency at a certain point in time.
Well, yeah, at a certain frequency, you would have a 0. Whether that 0 is in the numerator or the denominator, we call it a pole or a 0.
So the 0 is in the numerator?
Well, when the frequency is equal to 0.1, I have a 0 in the numerator. When it's equal to 5, I have a 0 in the denominator. Okay. So let me lay this thing out here. I'll just start in the middle with, well, actually I have, I'll start here at about 0. And I'll say 1, 2, 3, 4. I'll say this is 10 and 20, 30, and I think 40 should do this. And minus 10 and minus 20. And then we're going to, we'll start this at 0.1 and 1.0. This would then be 10 and 100 and 1,000. And that'll probably be enough for us. So if I look at the terms on this, what am I going to have? I'm going to have to deal with, I'm going to have a positive term that's going to be 20 times the log of 1 plus j omega over z1, which is that 0.1, right? So that's one term. I'm going to have one that is, well, I'm talking about the positives. I'm going to have a positive 20 log of k naught, square root of 10. How about the negative terms? I'm going to have a minus, because it's in the denominator, 20 log of omega. And then I'm also going to have a minus 20 log of 1 plus j omega over the pole. That's that 5, right?
These are all just things we have to plot.
Yeah. I mean, they came from the terms. I mean, we have 2 terms in the numerator, 2 terms in the denominator, right? Okay. So let's see. If I go to plot this one, that's probably the easiest one. 20 log square root of 10. The log of square root of 10 is a half. 20 times a half gives me 10, doesn't it? So I can put that in there. That's 20 log of root 10. So that's that one. The other one that may or may not be easy, I guess once you've done this once, then it's probably a little easier, is looking at that. Minus 20 log of omega. What's that going to be? Well, one thing I always look at these is when omega is equal to 1. That ought to be an easy point to find, right? What's this thing going to be equal to? Let's see, the log of 1 should be 0, shouldn't it? Okay, so the term is equal to 0. So I got a point here when omega, this is omega down here in radians per second. When it's equal to 1, I have a value of 0 right there. And what's it going to do? It's going to go downhill at 20 decibels per decade, right? So at 0.1 it should be at what? 20? And at 10 it should be at minus 20. Okay, so I have that, and I guess up here it'd be minus, or 40. So there's that one. So maybe I'll label that here, minus 20 log of omega. So we've got that one. And then we have these. What is this one going to do? This one, because it's a positive, it's going to go over and it's going to turn up, isn't it? And where's it going to turn up at? 0.1. And while we're talking about this kind of stuff, what's this one going to do? It's going to go over and it's going to turn down because it's negative. Where's it going to turn down at? 5. Okay. So for small values of this thing, it's going to take on a 0 value, isn't it? And then we said at 0.1, it was going to turn and do what? Go up 20 decibels per decade. So I should go through that point there. And I'd be up here, wouldn't I? There we go. So that's that one. And lastly, we have that one. It's going to go along at 0. And then we're going to get to 5. Maybe we had better find 5 here. This is 1 and this is 10. So this is what we 2, 3, 4, 5. So we'll right here. We'll get to that point. It's going to turn down at 20 decibels per decade. So it should be at what, minus 50. There's 10, 20, 30, 40, 50. So we should be right there. Like that. So then it's just a matter of adding those things up, right? So what's that going to look like? I mean, you can look at any point in time here. For instance, right here, I have 0, and I have another 0, and then I have 10, and I have 40. So where's that going to put me? Actually, up here at 50, isn't it? Okay. And then I just have this constant value should come down. At this point, I should have a value of what? 30? Is it going to follow along there? I think so. And then what happens? I got this one going down, but I got this one going up, so that's going to cause me to go straight for a while, right? And in fact, I'll go straight until I get over to 5, right? And then what happens? I got another one going down, so that's going to cause me to turn down at 20 decibels per decade. So I go from 5 to 50, 30, so I should be at 10 at 50, right? Yeah. There we go. So we just put those all together. Good with that?
Is the slope of that solid line twice the slope of negative 20?
The slope of this solid line is actually the same as the slope of these other pieces. Yeah.
The negative 20 log 1 plus j omega over 5.
Okay, this one?
Yeah, so it starts off going straight and then it angles down at 5.
Right.
And then you said it will go potentially 20 downwards per decade.
Mm-hmm.
So wouldn't it hit 20 at 5?
Well, let's see. At 5, we have the corner, right?
Sorry, I'm at 15.
So it should be at 50, because that'd be the order of 10.
Okay, sorry. I thought it was going all the way over to 140.
No, my graph paper on this one is almost too big. So. Other questions?
Where does it intersect 50? Right there? Is there a specific spot? Is it 10 and 50?
Right here?
Yeah.
Yeah, well, if I'm up here at, if I turn the corner at 5, if I'm at 0 and I turn the corner at 5, and then at 50 I should be at minus 20.
Yeah, I'm asking in relation to the solid line.
Oh, the solid line?
Slope, where does it, what were we aiming for?
At 50 I should be at 0. Other questions? Okay. Now we know certainly that nature does not like a hard corner, so we would expect the real curve probably to have some roll over there, some rounding off there. But that's not a bad approximation, and I'd like to speak a little bit to how we could correct at the corners if we wanted to. So let me talk about that. So if you're looking at the correction of the corners, and I don't spend a lot of time worrying about this. If you want the graph this close, just put it on a computer and you'll get the exact thing. But if you wanted to take this straight line approximation and make it a little better, if you say the corner frequency, you can correct this with, on your decibel graph, you're going to add or subtract 3 decibels. If it's a half the corner frequency, you're going to change the amplitude by plus or minus 1 dB. And if it's at twice the corner frequency, you're going to change the amplitude by plus or minus 7 dBs. So let's see how that looks on this thing. At the corner, we would in this case need to add 3 decibels, okay, which makes sense. At half the corner frequency, we're going to add 1 decibel, and at twice the corner frequency, we're going to have to add 7 decibels. Okay. I think that should work. Yeah, I mean, if I were to put this in a graphical sense, it's going to look something like this. If I have a graph and it's going into the corner, we'll say that that's the corner. The corner is going up, or this also works if the corner is going down. So you're trying to get this approximation in here like this. Okay. So at so here you would have plus or minus 1. Here you would have plus or minus 3. And here then you would have plus or minus 7.
Is that the frequency in the y-axis that we're looking at?
This would be omega.
So at that vertical line that you drew with the one above it, that is half of the dotted line?
Yes. Well, this is at half the frequency. This is going to be the corner, and this is half the corner, and this is twice the corner.
Meaning, what's the magnitude of the corner frequency that we're talking about?
Well, whatever this corner frequency is, for instance, in this case, the corner frequency here was 0.1, and the corner frequency here was 5. So you'll see people talking about this a little bit. I think if you wanted that exact, I'd start looking at a computer. I think the straight line is nice because it's just easy to do it quick by hand. I probably wouldn't clutter it up with this, but I mentioned this just in case you see someone else doing it. Questions with that? I'll double check that. If you were to take the function and actually graph it to deal with, because we've been fairly abrupt in this. We said that this turns right at the corner. Well, it doesn't turn right at the corner, and if we were to graph that more carefully, we would see those differences. Well, let's try a couple more of these, or I guess we'll go back to these pictures here. I think this is the one that we did last time, remember? And we actually went and looked at a couple values. We took the transfer function. I don't know if you remember, but to recap this, we took this transfer function, which is fairly involved, and we evaluated it at 50 radians per second, and we evaluated it at 1,000 radians per second. We came up with these answers in decibel, and we plotted them on the graph there. And when we found that we were sufficient distance from the corner, we found that the point was right on the graph. In fact, I moved this point down a little bit because it would have got lost in that line. If we were close to the corner, then we saw some problems here. We were off by just a little bit. Instead of 38.9, we were at 40, but still not a bad approximation. So you can see your values, your accuracy is not as good at the corners as it is away from the corners. Well, I'm not going to get too carried away with the corners from here on out, but I would like to practice on some more of these. I guess I need to number these pages. This is 3. So I'd like to try this one, which we're going to start out with the function, the transfer function 10 times 0.1 j omega plus 1 divided by j omega plus 1 times 0.02 j omega plus 1. So it's a little different form than we've seen. I think we'll be okay. So I'm going to start out, I need to go about plus and minus 60. So I'll start out here at 0. Take this as minus 10. Yeah, hopefully that'll give me enough. Okay, and the frequencies, let's see, what range am I going to be? I'm going to be somewhere around, where's my corner frequencies? I should have a corner frequency at 1. I should have a corner frequency at 10. And I should also have a corner frequency at what, 50? Is that right? I mean, if I look at these things, I'm going to look at 0.1 j omega plus 1. What's that going to do? It's in the numerator, so it's positive. So we're going to have a corner that goes like that. And where's that going to happen? Well, what's the frequency to make these terms look the same? If omega is equal to 10, yeah, so it's going to go up at 10. So then I'm going to have another one with minus, because it's in the denominator, but minus j omega plus 1. So that's going to turn down. Where's that going to turn down? 1, great. And then we also have a minus 0.02 j omega plus 1. So that's going to turn down at what? What's 50 times 0.02? Should be 1, shouldn't it? So we're going to have this at 50, aren't we? Good. Okay, so we've got all of this. I guess the last term to look at is what is 20 log of 10. What's that going to be? Should just be 20, shouldn't it? Log of 10 is 1. So we should get 20. So we can do this. We're going to have this line here at 20. So there's that one. Let me label that.
We always start with the log.
When you say start with, I mean we could start.
Starting at 20. And,
well, if this k naught, I think the other example, what was k naught? K naught was the square root of 10, so the log turned out to be a half. Half of 20 gave me 10. Yeah, I mean we could start with any of the. I mean we're going to have to add them up. So I guess I thought maybe it was the easiest, but let's see. We got 20 log 10. And then this one over here, that's going to be at 0, right? And turn up at 10. So let me start this at 1, and we'll do 10, and we'll do 100, and we'll do 1,000. So if I go over to, so if I go over to 10, it's going to go to 10 and turn up, isn't it? Well, they always rise with, if they're at a first order, they're always going to rise at 20 decibels per decade, right? If it's a squared term or something, then we're going to be a little different. We've got some examples of those. We're going to tackle this a little bit like we did the Carnot maps, just doing different examples that will hopefully illustrate different things. Okay, yes?
What would be just your word? Will those always start at 0?
Yeah, because you have to look at low values of frequency. That term goes away. So what's the log of 1? Times 20? 0. Okay. This log always troubles people. I think nowadays in math they probably do a lot better job of explaining what the log is. I mean, in my day they told you about log, and well, log was to undo e, natural log, right? If you had e, take the log of it. If you have the log, you take the exponent. But if you play around with it with some values, I think you'll get hopefully fairly comfortable with this. Well, when omega is very small, this term is not important, right? Okay. When omega is large, this term is not important. Okay, so where does that transition happen? Well, that transition happens when they're equal to each other, right? So how do I get this term equal to that term? So the question is when does 0.1 omega equal 1? What does omega have to be? Well, J is just telling us that's the complex portion. Okay, and I of course did the same for these. This one is pretty easy. Let's do it then. We're going to go over here 0, turn down at 1, right? So I should probably label these 20 log of 0.1 j omega plus 1. This will be 20 log of j omega plus 1. No, it can't be that. This is plus 1. This is 0.1. So we've got those two. This last one's going to turn at 50. It's going to turn down at 50. So there's 10, 20, 30, 40, 50. That's 50. So then we're going to be over here at 500, 200, 300, 400, 500. So there is 20 log of 0.02 j omega plus 1. So then I just have to put them all together. So if I take this 0 plus 0 plus 0 plus 20 gives me 20, right? In fact, that's the same until I get to this point. And then what's it do? It's going to follow this down to there. And then what happens? This starts going back up, so it's going to start to go straight again, isn't it? to there, and then what happens? It'll actually turn down and follow this one, won't it? Yeah, good.
Wait, you just said it goes up, but you could restrict on this between 10 and 50.
Okay, so I'll go over this again. You got, this is any point along there. You got 0 plus 0 plus 0 plus 20, so you're good there. And now this one starts to go down because this one's going down, right? Okay. So I've got this. And now I get something changes again. And you don't, I mean, once you make this decision here, you can just keep drawing that line straight until something changes, right? So we get here, and instead of this being 0, it starts to go up. So if I'm pointed down and this one starts to go up, that'll turn me back so that I'm straight, right? And then...
But also isn't it because of the negative slope, right, at the same point? Yeah, okay. We just said the same thing.
I think so. And this one's a little deceiving because I drew the heavy line on top of this, but it actually then, because this one's going down, it then now starts to follow that.
Because you have 2 negative slopes on one side.
Right. So we have something like that. Questions with that? Well, we're just adding up the lines. I mean, at any point along here, well, I don't so much look at the slopes, but the values. Yeah, I mean, at this point here, I take this, and then this is a negative value, and that's a positive value, so I'm going to get that value in the middle. I mean, you're right. If you want to draw this faster, you can look at the slopes, but really what you're doing is you're adding those curves up. Other questions? Well, let's try another one. So this one, yeah, this is kind of a nice one. Let's try 25 times j omega plus 1 divided by j omega squared. That's kind of nasty. 0.1 j omega plus 1. Okay. So what are we going to have there? Well, we're going to have the 20 log of 25, right? What's that? I think I got to grab a calculator for that, right? Log of 25 is not particularly nice. You get about 27.9, 28, somewhere in there. I guess that's 958, 959. So we're just going to say that's 28. Okay, that's where I got that. Okay. This one's not going to be much trouble because we're going to have plus 20 log of j omega plus 1. What's that going to do? That's our typical business with the corner, right? It's positive, so the corner is going to go up. Where's the corner going to be? Yeah, 1. Great. Okay. Let's tackle this other one in the denominator. 20, so it'll be negative because it's in the denominator. Log of 0.1 j omega plus 1. So where's that? That's going to turn and go down because it's negative. Where's that going to happen? Should be 10, yeah. Good. You're getting this figured out. Mm-hmm.
Just what the 20 log just what it's resulting in, we're finding omega where it'll equal that other side of the addition or subtraction.
At the corner?
Right, yeah, we're just finding omega so that it will equal 1, which is on the other side, right? Or that 0.1 times.
We're trying to find out where these two are the same.
So when they're the same, that's going to be, say, 2. What is 20? Then we would be evaluating 20 log of 2, right?
Well, no, it's going to be, because this is J.
Right.
So you're going to have root 2 in there.
Right. So then what is that evaluated to? And does that
Well, that's why it's off at the corner. I mean, it doesn't have a really nice corner like this. It's actually like this. Mm-hmm.
Will we ever have an equation that has anything other than 1?
Other than 1.
Yeah, like JW plus 1.
Well, you can get rid of the other term by factoring it out. We did that on. Okay, so these hopefully are not too bad. The kind of the ugly one in this one is that j omega squared. So let's go and look at that. So 20 log of j omega squared, which, let's see, when I square it, I can bring it out. Wouldn't that be the same as saying 40 times the log of j omega? Will you buy that? Should be able to. That's one of the rules of logs. Yeah, it should be, it's in the denominator, so yeah, it should be negative. So now, what if omega is equal to, let's pick an easy point. If omega is equal to 1, what do I end up with? Well, the log of 1 is 0, so I end up with the term being equal to 0, right? And it's going to go down at what? Minus 40 decibels per decade. Okay. So we should have a handle on those. I'll run from about positive 40 to negative 40, so I'll just take 0 here at the middle. Let's see how that treats us. And let's see, where are our corners? At 1 and at 10. So we can probably just start this at 1.0, take this at 10. That is 100, and we probably don't need the rest of the graph. We should be okay. So where are we here? We've got a line at what? 28? So there's 20, there's 30. So pretty close to that. We'll have that term 20 or plus 20 log of 25, which turned out to be about 28. Then if I do this next one here, we're going to go over at 0 and turn up at 1, right? So over at 0, turn up at 1. So that's this one. Positive 20 log of j omega plus 1. And So you've got those two. If we look at this one, minus 20. So I'm going to go over at 10. It's going to turn down, isn't it? 20 decibels per decade. So there's minus 20 log 0.1 j omega plus 1. And then the last one over here. So we said when omega was equal to 1, it had a 0 value, so it's going to go right through there, and it's going to do it at a slope of what, 20 decibels or 40 decibels per decade, isn't it? So if this is back here at 0.1, I would be up at what, 40? Yeah, so I wish there was a little bit. I'll take this point up here at 40. Okay, and at 10 I'm going to be at what? Minus 40, right? Like that. So that is the term minus 40 log of j omega. So what are we going to have in there? Yeah. I got to add this to that. And maybe I'll start at 1.
Oh, so you have 30 to negative 40. 28 to negative 40.
Right. Well, 28 to, well, at this point, yeah, here you would have to add 28 to 40, so I'm well off the graph there. Yeah. But if I come back to this point, if I start at 1, what I'm going to be? These are all 0, so I'll be here, right?
Isn't that positive slope is half of that angle? So
Yeah, I've just established my point here. Okay. So this is 0, that's 0, that's 0. So I know I'm going to have that value there, right? And then this slope is a lot larger than that slope, so it's going to be traveling down, right? And what am I going to get over here at 10? We'll end up at 10.
is that going to be 28 minus 20?
Well, I'm going to be at 20, and 28 gives me what, 48 minus the 40. So I'm going to be at about 8, right? I'm going like that. And then what am I going to be over here? I'm at minus 20, and I start to get off the scale over there. So this is going to come in like this. I'll do something like that. Look at that. Yeah.
So why did you extend the minus 40?
Extend the minus 40.